Tesla has finally provided its first concrete timeline for equipping the Tesla Semi with full self-driving. The announcement comes as Tesla prepares to begin mass production at its dedicated semi-factory in Nevada, which is designed to produce up to 50,000 trucks annually. At the same time, customer orders and reservations have already surpassed 1,000 units from major fleet operators, including PepsiCo, DHL, Walmart Canada, Cisco, Martin Brower, and several others. During Tesla's Q2 2026 earnings call, Elon Musk confirmed, "We expect to get self-driving working on the Tesla Semi probably around the end of this year or early next year. I just don't want it to be a distraction on the march of nines of safety for self-driving on the Model 3, Model Y, and Cybercab. It will definitely be working next year." Besides, the most significant recent update to the Tesla Semi is not merely a cosmetic refresh, but a radical overhaul of its underlying chassis architecture. Rather than relying on a rigid one-size-fits-all model, Tesla has evolved the Semi into a versatile platform offering two distinct battery configurations, a 300-mile standard range variant and a 500-mile long-range variant. To accommodate a battery pack capable of propelling a fully loaded Class 8 truck for 500 miles, Tesla introduced a subtle yet crucial design modification, a slightly extended chassis section positioned between the rear wall of the cab and the primary drive axle. While visually minor, this physical stretch expands the internal battery compartment without requiring a ground-up redesign of the entire vehicle. Both the 300-mile and 500-mile variants utilize the exact same central seat cabin, panoramic windshield, aerodynamic body panels, suspension geometry, and assembly tooling. By maintaining high parts commonality across both models, Tesla drastically reduces manufacturing complexity at its Nevada manufacturing facility, preserving factory floor footprint while scaling toward an annual production capacity of 50,000 units. In the United States, federal mandates permit zero-emission Class 8 electric trucks to operate at a maximum gross combined weight rating of 82,000 pounds, which is a 2,000-pound allowance above traditional diesel rigs intended to offset heavy battery packs. However, adding raw battery capacity introduces localized mass that can easily violate strict per-axle weight limits if improperly balanced. By distributing the expanded battery modules longitudinally along a stretched wheelbase on the long-range model, Tesla effectively disperses the additional mass evenly across all three axles. This structural load balancing provides four vital operational benefits. It maximizes cargo carrying capacity without exceeding regulatory axle caps, improves high-speed directional control and mitigates rollover risk on uneven interstates, reduces mechanical stress on airbags and structural crossmembers, and minimizes tread scrubbing to lower fleet maintenance costs. Electric semi-trucks face severe aerodynamic drag penalties at highway speeds compared to passenger vehicles due to their massive frontal surface area. To maximize real-world range without inflating battery size to impractical limits, Tesla retained the Semi's ultra-sleek, bullet-inspired exterior shell. The Tesla Semi achieves a drag coefficient far lower than conventional flat-nosed or long-hood diesel trucks. Features like sealed underbody fairings, flush-mounted side skirts, and contoured cab-to-trailer air vanes allow the truck to slice through ambient air with minimal turbulence. Because aerodynamic resistance grows quadratically with vehicle velocity, preserving this low drag profile ensures that expanded battery capacity translates directly into usable miles rather than overcoming atmospheric resistance. Underneath the chassis, both Semi variants rely on a proven three-motor electric drive system capable of generating a peak output of 800 kilowatts or roughly 1,070 horsepower. Rather than running all electric motors continuously, Tesla utilizes intelligent power management. At steady highway speeds, two of the three motors are mechanically disengaged to eliminate parasitic drag, allowing a single high-efficiency motor to maintain momentum. When navigating steep mountain grades, overtaking slower traffic, or hauling maximum gross weight from a complete stop, the remaining two acceleration motors engage seamlessly within milliseconds. This automated torque vectoring yields effortless acceleration, taking a fully loaded 82,000-pound vehicle from 0 to 60 miles per hour in just 20 seconds, while preserving high energy economy during routine flat highway transit. The strategic introduction of a 300-mile standard range model directly addresses a fundamental reality of the freight industry. A vast majority of commercial truck routes do not require extreme driving ranges. According to transportation statistics, a massive percentage of Class 8 vehicles in North America travel under 250 miles during a standard daily operational shift before returning to a central depot overnight. For these regional distribution networks, purchasing a 500-mile battery pack creates unnecessary capital expenditure and carries dead weight that reduces net payload. By offering the 300-mile standard range Semi, Tesla provides local distribution fleets such as grocery store suppliers and port drayage operators with a lighter, more affordable vehicle that can recharge during off-peak night hours. Conversely, the 500-mile long-range model provides interstate carriers with the endurance necessary to complete long regional legs without mid-shift delays, effectively segmenting the market and accelerating electrification across diverse logistics sectors. While structural upgrades establish the physical foundation of the Semi, its true competitive advantage lies in its transition toward full autonomy. During Tesla's Q2 2026 financial call, Elon Musk outlined the first concrete timeline for bringing full self-driving capabilities to the commercial truck, stating that the company expects to get self-driving working on the Tesla Semi around the end of this year or early next year. Although industry analysts suggest early 2027 represents a more realistic timeframe for widespread commercial rollout, this announcement confirms that Tesla is expanding its autonomous software stack beyond consumer passenger cars and into heavy freight. The delayed implementation of FSD on the Semi has never been caused by physical sensor deficiencies or computing bottlenecks. Rather, it represents a deliberate software prioritization strategy. Tesla's autopilot engineering team remains laser-focused on refining FSD for high-volume platforms, specifically the Model 3, Model Y, and Cybercab, which collectively generate billions of miles of real-world driving data. Musk refers to this process as the March of Nines of Safety, where software engineers systematically drive the system's reliability metric from 99.9% toward 99.9999% precision. By deferring semi-specific FSD development by roughly 6 months, Tesla ensures that its core AI neural networks reach ultra-high safety baselines on lightweight passenger vehicles before applying those learned weights to an 82,000-pound commercial vehicle where software errors carry exponentially higher safety risks. Unlike traditional truck manufacturers that must retrofit third-party LiDAR arrays, radar domes, and external computing racks onto existing diesel chassis, every production Tesla Semi is manufactured autonomous-ready from the factory floor. The vehicle features Tesla's AI Force suite, consisting of 10 high-resolution exterior optical cameras providing full 360-degree surround vision and a single cabin-facing camera for driver attentiveness tracking. At present, this vision processing pipeline drives standard active safety features like automatic emergency braking, forward collision warning, lane departure warning, and lane keeping assist. Because the sensing hardware and central processing units are built directly into the vehicle architecture, unlocking full point-to-point autonomous operation will require no retrofits or dealer visits. When the Semi-specific neural networks pass internal safety benchmarks, the full self-driving capability will be deployed fleet-wide through an over-the-air software update. Recent field activities strongly indicate that real-world testing of the Semi's autonomous software stack is accelerating. Over recent months, multiple Tesla Semi engineering prototypes have been documented navigating public roads around Sunnyvale, California, and near the Fremont factory, carrying large roof-mounted sensor calibration rigs. Tesla historically employs these specialized calibration rigs to establish ground-truth physical measurements and validate camera alignment prior to launching major software updates, a validation process previously witnessed before FSD launches on the Model S, Model 3, Cybertruck, and Cybercab. Autonomous capabilities are only as effective as the charging infrastructure supporting them. To prevent long charging downtime from eroding the operational efficiency gained through driverless transit, Tesla developed the Megacharger ecosystem. Operating at a peak power delivery rate of 1.2 megawatts, Megachargers utilize liquid-cooled charging cables and high-voltage connectors to inject up to 70% of total battery capacity in roughly 30 minutes. This rapid energy replenishment aligns with mandatory human driver rest breaks, ensuring continuous fleet movement across national supply corridors. The convergence of a modular electric truck platform, ultra-fast megacharging, and full self-driving software will trigger a profound transformation across the global supply chain. The commercial trucking industry faces a severe driver shortage driven by grueling work conditions, an aging workforce, and demanding lifestyle requirements. By introducing autonomous driving capabilities, fleet operators can run continuous long-haul hub-to-hub routes without human fatigue constraints, reserving human drivers for complex local deliveries and last-mile operations. To fully appreciate the scope of this industrial shift, one must analyze the broader environmental and municipal impacts of replacing legacy Class 8 diesel engines with autonomous electric powertrains. Heavy-duty trucks account for a disproportionate percentage of total transportation emissions relative to their total numbers on the road. Diesel exhaust produces particulate matter and nitrogen oxides that contribute significantly to urban smog and respiratory illnesses in communities located near major freight corridors. By eliminating tailpipe emissions entirely, the deployment of 50,000 Tesla semis annually will displace millions of barrels of diesel fuel consumption every year. Furthermore, the operational quietness of electric powertrains enables overnight freight deliveries in urban zones where strict noise ordinances currently ban heavy diesel transit during evening hours. This shift allows fleet managers to bypass daytime gridlock, flattening traffic congestion curves in major metropolitan centers and lowering overall energy consumption per ton mile. Moreover, the integration of autonomous software into heavy transport introduces unprecedented levels of highway safety. Commercial truck accidents, often caused by driver fatigue, distraction, or delayed reaction times on high-speed interstates, result in thousands of fatalities annually and billions of dollars in insurance liabilities. Tesla's FSD Vision Stack processes visual inputs across a full 360-degree field of view continuously, reacting to dynamic road hazards, sudden braking events, and adverse weather conditions with sub-millisecond latency. By eliminating human error from interstate freight transit, autonomous semis will drastically reduce highway collision rates. This safety paradigm shift not only preserves human lives but also radically alters the insurance landscape for commercial logistics, lowering premiums and removing a massive risk variable from corporate balance sheets. The digital architecture of the Tesla Semi also enables seamless integration into modern enterprise resource planning and smart logistics networks. Every vehicle operates as a connected node within a broader telematics ecosystem, transmitting real-world battery health, tire pressure, motor efficiency, and location data back to central fleet dispatchers in real time. Predictive maintenance algorithms can identify component wear before mechanical failure occurs, scheduling automated service stops at specialized Tesla service hubs without disrupting supply chain schedules. When combined with autonomous routing software that dynamically calculates optimal paths based on live traffic conditions, weather forecasts, and Megacharger availability, the Tesla Semi optimizes logistics workflows at a level of mathematical precision that legacy fleet management tools simply cannot match. In conclusion, the Tesla Semi is no longer an unproven technology concept confined to investor presentations or prototype showcases. Through a quiet yet radical engineering evolution, Tesla has transformed the Semi into a modular, production-ready commercial vehicle platform capable of meeting the varied demands of regional distribution and long-haul interstate transportation. By offering dual battery configurations, optimizing weight distribution across a stretched chassis, maintaining superior aerodynamic efficiency, and embedding state-of-the-art AI-4 self-driving hardware, Tesla has addressed both the physical and economic barriers of commercial electrification. As software validation accelerates and Megacharger networks expand across key global shipping lanes, the Tesla Semi stands poised to fundamentally disrupt the global freight landscape, delivering a cleaner, safer, and infinitely more efficient future for global trade.